Welcome to the deep dive. Today we're going to really dig into a core challenge for robotics. How do we teach robots complex skills just by showing them?
Yeah, it's a huge area. And specifically, how do we do it when the examples we give them, well, they aren't always perfect?
Right. It's like imagine wanting to learn a really intricate piano piece, but all you have are a couple of short, maybe slightly out of tune recordings. You wouldn't become a concert pianist from that alone.
That's a great way to put it. And that brings us right to the research we're looking at today. It's a paper called SkillMimic V2, Learning Robust and Generalizable Interaction Skills from Sparse and Noisy Demonstrations. It's coming out of SIGGRAPH 2025, and it offers a really clever take on this exact problem.
Okay, so let's break down that problem a bit more. The fundamental issue you're saying is that if I show a robot how to, I don't know, flip a pancake or tighten a screw, my demonstration might be missing steps, or it might be jerky, noisy, as the paper calls it. Maybe I only show a couple of key moments.
Exactly. Sparse, disconnected, noisy. Those are the key words. It's like those IKEA instructions you mentioned earlier. If half the pictures are missing and the others are smudged.
Yeah, you'd probably end up with a wobbly bookshelf if you're lucky.
Right. And for a robot, this isn't just annoying, it's often a complete roadblock. Existing methods, particularly in reinforcement learning from interaction demonstration or RLID.
RLAD, okay. That's where they learn from examples and then trial and error.
Precisely. But if those starting examples are flawed, the robot struggles. It can't perform the skill reliably, and crucially, it can't generalize. It can't adapt if things are slightly different.
It gets stuck just trying to mimic the flaws, maybe?
And that's a big part of it. Think back to that dance analogy again. Trying to learn from just a few shaky clips. You miss the flow, the transitions, how to recover if you stumble slightly.
Makes sense. And the paper actually shows this, right? With figure 2.
It does. It clearly illustrates how trying to perfectly copy a demonstration that has, say, physically impossible movements or just small errors, it's a dead end.
Even tiny errors, like being a centimeter off.
Yeah, they give an example, a hand being just 2 centimeters off when grabbing something. That tiny deviation can cause the whole attempt to fail. It's what they call the chain break problem sometimes. An early error ruins everything downstream.
Wow. Okay, so the old way is brittle. How does SkillMimic V2 get around this? What's the big idea?
The core insight is actually quite elegant, I think, it says. Okay, the demonstrations aren't perfect, they're just scattered snapshots, but there are countless physically possible ways to connect those snapshots.
So there isn't just one way to do the task based on the demo.
Exactly. There's a whole continuous space of valid movements around and between the demonstrated points. Think of the demos as islands. SkillMimic V2 isn't just about hopping between those islands.
It's about learning to navigate the ocean between them.
That's a perfect way to think about it. It intelligently fills in the gaps and explores nearby possibilities. And it does this using some really neat data augmentation techniques.
Okay, let's get into those. The first one is the Stitch Trajectory Graph, STG. What's that doing?
So the STG is all about building those bridges between different skills you might have demonstrated separately.
Right, like maybe I showed the robot how to dribble a basketball and then in a totally separate demo, how to shoot.
Exactly. STG helps the robot figure out, okay, how can I physically transition smoothly from this dribbling motion into a good shooting stance, even if you never showed that specific link?
So it finds plausible intermediate movements.
It does. It looks for states in one demo that are physically close or reachable from states in another demo and figures out a feasible path. You can see a visualization of this in figure 3 of the paper. It really expands the robot's repertoire.
That makes a lot of sense. So it learns not just the skills, but the connections. What about the second technique? State Transition Field, STF. Sounds more detailed.
It is. STF focuses within the neighborhood of the demonstrated trajectories. It essentially creates a map for the robot. If the robot finds itself in a state that's close to one it saw in a demo, but not exactly on it.
Like if it bobbles the dribble slightly.
Precisely. The STF gives it guidance, a kind of vector field, showing, okay, from this slightly off position, here's a physically plausible way to move to get back on track or continue the skill.
So it builds in robustness to small errors, helps it recover.
Exactly. It makes the learned skill much less fragile.
But I saw a mention of overlapping neighborhoods being tricky. What's that about?
Yeah. That's a potential pitfall. Imagine if the robot is in a state that's sort of close to 2 different parts of the demonstration, Maybe one part where it should be moving left and another where it should be moving right.
It gets conflicting signals.
It could, yeah.
Yeah.
The STS is designed carefully to ensure that for any given state near the demos, there's unique, clear direction suggested. It avoids that confusion.
Got it. And they also use something called masked states. What are those for?
That's another clever trick to handle larger gaps in the data, if 2 points in a demonstration are quite far apart in time or space.
With no intermediate steps shown.
Right. They can insert these masked states in between. They're like placeholders. The learning process then has to figure out how to in-paint or fill in a physically valid sequence of movements to bridge that gap.
So it's basically forcing the system to learn plausible connections even when the demo didn't provide them.
You got it. It's all about generating richer, more complete data for the reinforcement learning process.
Okay, so STG connects skills, STF handles local variations and recovery. That generates better data. But how does the robot actually learn from this augmented data efficiently? That brings us to adaptive trajectory sampling, ATS.
Yeah, ATS is about focusing the learning effort. The insight here is simple. Not all parts of learning a skill are equally hard.
Like learning to ride a bike, the balancing is harder than the pedaling, maybe?
Exactly. So ATS dynamically monitors where the robot is struggling the most during training, which parts of the trajectories are causing errors.
And it makes the robot practice those tricky parts more.
Pretty much. It increases the sampling rate from those challenging segments. This helps prevent that chain break problem we mentioned earlier, where one small mistake early on derails everything. By focusing on the hard parts, the robot builds a more reliable skill overall.
That's smart, like targeted practice. Okay, one more key component. The history encoder, HE. This is for skills that depend on, well, history, right? What happened before.
Right. Think about tasks where the same situation might require different action depending on what just happened. The example you gave earlier, holding a ball for a specific time before passing.
Okay. A standard RL approach might get confused there.
It often would, because the immediate state looks the same, but the required action is different based on the past. The history encoder tackles this.
Wow.
It takes a sequence of recent states, like the last few observations the robot made, and it learns to compress that into a compact history vector.
Ah, like a summary of the recent past.
Exactly. And that history vector is then fed into the robot's control policy along with the current state. So the robot's decision isn't just based on now, but also on a learned representation of what just happened.
And the cool part is it learns this representation from the data. We don't have to manually define phases or timing.
That's the key. It's data-driven. And they pre-train this HE using behavioral cloning first, which helps make the main RL training process more stable.
So it's like giving the robot a learnable short-term memory. Very useful. Okay, this all sounds incredibly promising on paper. How did SkillMimic V2 actually do in tests?
They really put it through its paces. They used the Isaac Gym simulator, which is known for pretty realistic physics, and tested it on 2 main data sets.
Right, the basketball one. Ball play M.
Yep, ball play M for basketball skills, dribbling, shooting, layups, that kind of thing. And also Parahome, which has more everyday household interactions. You can see examples of the learned skills in Figure 1 of the paper. They look quite impressive.
And compared to other methods, like the original SkillMimic or DeepMimic,
the improvements were really substantial. Across the board, pretty much. Let's talk numbers a bit.
Okay.
First, success rate, SR. Just, can the robot actually do the task correctly? They saw improvements often in the range of 40 to 50% over the prior state-of-the-art.
40 to 50%, that's huge. That's the difference between failing half the time and succeeding most of the time.
Absolutely. For some tasks, like the layup skill shown in Figure 4 or placing a pan in Table 2, they got close to perfect success rates.
Wow. What about adapting? Generalization?
That's measured by ENSR, or generalization capability. Here they saw over 35% improvement. This means SkillMimic V2 was much better at succeeding even if the starting position was a bit off, or if small errors occurred during execution.
And recovering from bigger mistakes. Robustness.
Yeah, they looked at robustness to perturbations too. Figure 4 has a nice visual. You see the robot get knocked off balance while dribbling, but it recovers and continues the skill. That's the STF and the focus learning from ATS likely helping there.
And those transitions between skills, did the SDG pay off?
It really seemed to. The transition success rate, TSR, was very high. Table 1 and Figure 7 show the robot successfully switching between different basketball skills, like dribbling into a shot, even when that specific transition wasn't explicitly demonstrated.
So it learned the links. It sounds like all these pieces, STG, STF, ATS, HE, really do work together. Did they check that?
They did. Standard practice in this kind of research is an ablation study. You take the full system and then test versions where you remove one component at a time.
To see if each part actually contributes.
Exactly. And Table 3 shows the results. Removing any of STG, SDF, ATS, or HE led to a noticeable drop in performance, confirming that each one is adding value.
So the whole package is more than the sum of its parts, in a way.
It seems so. They also did other tests, showed it works well even with less demonstration data, which is great.
Data efficiency, nice.
Yep. They showed it works for locomotion skills, too, not just object interaction, things like walking, running. It's robust to noise in the demonstration data itself.
Which is crucial for real-world application.
Definitely. And maybe one of the most striking results was the zero-shot in-hand reorientation.
Yeah, you mentioned that. Learning to manipulate an object just from a single grasp.
Basically, yes. They showed it could learn to reorient a cube in its hand using diverse grasps, learning this complex manipulation from just sparse examples of successful grasps, not full manipulation demos. That's figure 1D. It really hints at the generalization power.
That's pretty amazing. Okay, let's pull back a bit. For someone listening, what are the main things to take away from this deep dive into SkillMimic V2?
I think the biggest thing is that this work offers a really practical path towards robots learning complex skills from the kind of messy, incomplete examples that are easy for humans to provide.
It makes robot teaching more feasible.
Much more feasible. And the resulting skills are far more robust and adaptable than what we could get before. The way it intelligently adds to the demonstration data with STG and SDF and focuses the learning with ATS, it really makes a difference.
And the ability to link skills together.
Yeah, that smooth transitioning is key for versatility. Imagine a robot helper that can fluidly go from picking something up to carrying it, to putting it down precisely, without jerky pauses or failures.
And the history encoder giving it that context or memory.
Right, that opens the door to much more sophisticated behaviors that depend on timing or sequences of actions. It's learning that internal state, that memory, directly from the examples.
Okay, so to recap, SkillMimic V2 tackles learning from sparse, noisy demos. It uses the stitched trajectory graph, STG, to link different skills, the state transition field, STF, to handle variations and errors within skills, adaptive trajectory sampling, ATS, to focus learning on hard parts, and the history encoder, HE, for memory. Quite a package.
It really is a comprehensive approach.
Yeah.
And it makes you think, where could this lead?
Right. What are the broader implications?
Well, think about it. More realistic characters in games or films, sure.
Yeah.
But also much more capable robots in factories, maybe doing complex assembly. Or robots in healthcare, providing assistance. Even robots in our homes that can actually handle varied objects and tasks reliably.
When robots can learn robustly from imperfect examples and generalize, what new applications suddenly become possible that weren't before?
Exactly. What happens when teaching a robot a complex physical skill becomes less like programming and more like, well, just showing it a few times.
Yeah.
Even imperfectly. It's a fascinating direction.
Definitely food for thought. And if you want to see these robots in action, the basketball, the object manipulation, the researchers have videos on their project page. We've put the link, https://ingrid789.github.io SkillMimic V2, in our show notes. It's really worth a look.
Highly recommend checking out the videos.
Thanks for joining us for this deep dive.